What's up?
Mr. Bruce is best.
So today we're going to talk about what happens if you have a wire, you stick it in a magnetic field, and you make it move. All right? So, can't keep a straight face. All right. So, it turns out, let me move down to the picture because just giving you the equation is such an AP Physics B thing to do. All right. So, here's the basic picture. Let's say you had a magnetic field, and you had a wire in that magnetic field, and you took that wire and you slid the whole wire to the right at some speed. Everybody pull out your right hand. All right, right hand, the other right hand, you know. There you go. All right. Okay, so fingers go in the direction of the magnetic field, which is, which way? Into the page. Thumb goes in the direction of the movement, which is to the right. So what happens to the charges? Positive charges get pushed up in the wire. Now, if there was a wire connected here and here at the top and the bottom, and these wires were connected to, say, a light bulb, what would happen to the light bulb?
It go on.
The light bulb would glow. That'd be pretty cool, right? Yeah. You can actually make a light bulb glow just with a wire and a magnetic field. Did you know that?
Why don't we do that?
Yeah, it's actually the source of all the glowing light bulbs that we have in this room, except for the battery-powered ones. Yes?
The right hand roll, if it goes like this, it comes this way. Like on the left side of the wire,
Whoa.
Motion.
The motion is going to create the force, which is going to create the current. So you're taking the whole wire and ramming it to the right with your hand, right? And so you're pulling this wire to the right, which causes all the charges in the wire to move to the right. So positives would get pushed to the top of the wire, negatives would get pushed to the bottom of the wire. All right? And basically what that ends up doing is, if this were connected to a light bulb, you would have, therefore, since the positive gets pushed to the top, and then out here, it's going to be like, hey, I'm at a high voltage. I'm going to flow through this light bulb down to the low voltage side. And so you end up with a current loop as a result. All right? Now, by the way, if this wire was just a metal bar, not connected to anything, would the charges still move? Yeah. Would the positives still get pushed to the top of the wire?
Mm-hmm. Yeah.
Absolutely. But they wouldn't go anywhere once they were there. It would just be that airplane situation we talked about a second ago. Yes?
How powerful of a magnetic field would we need to create? Like, how much?
How much? Well, that's what this lecture is about, so we're going to go there.
Okay.
Yes?
Does it just have to be like the relative movement? Because what if the thing was there and then you have the field going like this?
Oh! Could you save that relative motion idea till Monday? Any thoughts you have right now, Sean, of relative motion, save until Monday. That is not only a great question, that is one of the best questions that you could possibly ask all year. But we're going to save the relative motion discussion until Monday. We'll just assume for now that the magnetic field is stationary and that the wire is moving. Got it? On Monday, ask that same question again. All right, so here we go. So the basic equation, the voltage difference produced from one side of the wire, this EMF thing, from the top of the wire to the bottom of the wire is going to be equal to BLV, or BLV sine theta. All right, that is something that you memorized last year. You had no idea where it came from. Now we're going to talk about where it comes from. BLV. Did you remember BLV? Yeah. E equals BLV, or voltage difference equals BLV. So here it is. Let's prove it. We're going to prove it two different ways. We're going to prove it with Faraday's law, and we're going to prove it with force on a charge. So here we go.
Is the theta between the B and the V?
The B and the V, yeah. All right, so method number one, Faraday's law. Let's say that this wire, or this metal bar right here, was connected in a complete current loop, right? and you are pulling this metal bar out of the field. So what's happening to this area? It's getting smaller. So according to Lenz's law, which way is the current going to flow? Pull out some right hands and figure this out. So what's happening to the field into the page? The flux into the page. It's getting weaker, right? Less and less flux.
So it's going to want to create a current that's going to...
It goes, it's same.
It wants to create an induced current that goes this way, right? Okay, good. So, so the voltage produced from one side to the other would be d phi over dt, Faraday's law, right? Mm-hmm. But flux is just BdA over dt. Agree?
Mm-hmm. Yeah.
Which is, if you think about it, the area of this thing, I'm going to scroll down just a little bit, is the length times the width, right?
Right.
But it's the length of the wire, but the width of the wire is the velocity times change in time of the wire, right? Because the width is changing. So LV delta T. So it's BLV delta T over delta T. What happens to the delta T's? They cancel out, and you're just left with BLV. So that's one way to prove this. There's a different way to prove that we talked about 20 minutes ago. It goes like this. Method 2. Let's say you just had a metal bar, and you were pulling it to the right through the magnetic field, just like the airplane problem. It's the exact same problem. What happens to the positive charges? They get pushed to the top, and the negative charges pushed to the bottom. Now, do they go past the end of the bar? No, not unless there's so much magnetic field, or the force is so strong that you get like sparks coming off. All right, so the electrons never actually leave the bar; they just go to the edge. All right. So, if that's true, then if you did a free body diagram of an electron on the bottom, the magnetic force down would balance the electric force up, so QVB equals QE, and you end up with the velocity times B equals the electric field. Scrolling down, EMF would be the electric field times the distance, or the electric field times the length of the wire, which is VB times L, or BLV again. Got it? So, this is the answer to the airplane problem, solved 2 different ways. Good, good? And in the end, you had memorized the equation BLV, but you need to be able to prove it in 2 different ways. Yeah, that's a pretty common question. Usually it would be the 3rd question in this series in the AP test, because the first question is always electrostatics, the second question is always some combination with circuits, and the 3rd question is always some magnetism question. And this would be a very common magnetism one on a free response. All right. So let's say you wanted to use a moving wire to create current. Blah, 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 blah. All you have to do is hook up a resistor or a light bulb. Guess what? The light bulb glows. And if you did this as a circuit, you know the induced current would be EMF over R, so the induced current would be BLV over R. Right? And what if you had 2 resistors in series? What would it be? BLV over 2R. What if you had 2 resistors in parallel? What would it be?
BLV over R.
2 BLV.
Yeah, 2 BLV.
2 BLV over R, because R is 1/2 as much. And is that it? And BLV, the fundamental equation upon which your quality of life depends. That's such an AP Physics B thing to say. Now, of course, we know it's Faraday's law. Because Faraday's law has calculus, and that's just better. So, that's it.